quasi-optimal way of reusing matrix by vector product. So that we multiply by one vector instead of multiplying maybe by different random vectors. So we stop on this. So the name Krylov comes from 1931, and the Andrei Nikolaevich Krylov, he was actually trying to compute. He did not know that this is an unstable way. He tried to compute the coefficients of the characteristic equations in this way. And that's why he suggested to use this method. Not for solving linear systems, for sure, but this was the way to compute the eigenvalues. So another motivation for using Krylov subspaces and finding the optimal solution there is that if you take the degree of the Krylov subspace equal to the dimension of the matrix, the solution will always belong to the corresponding Krylov subspace. The proof follows from the famous Henry-Hamilton theorem. So if you take the characteristic polynomial and put a matrix there, then you get exactly zero. Could also prove that. Seconds. That if you put a characteristic polynomial, put a matrix there instead of lambda. If you put a matrix in this form, well, this would be a bad idea. Right? So take determinant, then you get the coefficients, then you put a matrix in this, and then you get zero. Okay. So this so one way of proving this, okay, if A is Hermitian, then you can reduce it to the diagonal form, and then it is obvious. So if it's not Hermitian, you have to reduce it to Schur form, and again confirm that it's obvious. Yeah. Yeah. Yeah, so you get a polynomial, right? You get a polynomial with some coefficients. And then instead of the scalar argument, you put the matrix. With the same thing. For example, your polynomial is 5x plus 1. Then the matrix polynomial will be 5 times the matrix plus 1. The only requirement is that the coefficients come from the characteristic equation of the same matrix. Characteristic equation is just a scalar polynomial, but any scalar polynomial, you can put a matrix there instead of a scalar argument. And for a matrix, you get always zero.
For instance, if A is 2 by 2 matrix, then instead of lambda, I put another 2 by 2 matrix.
Not in this form. If you put it in this formula, then that would be a crazy form. Determine A minus lambda A times I. Stupid. So first, if it's 2 by 2 matrix, then you just compute the coefficients first, right? So then you get three numbers basically out of it. You give the matrix, you get three numbers, which is the zero coefficient, first coefficient, second coefficient. Then you get a polynomial, quadratic polynomial with some coefficients. And then you put into this quadratic polynomial, you just put the same 2 by 2 matrix, and you get exactly zero. This is this. So sometimes people say that you cannot have a polynomial of a matrix with a degree larger than the matrix size, because from this equation you can express a to the power n as a linear combination of the smaller powers of a. Yeah, you will get zero matrix. You can try it. There is a NumPy roots function, compute, and then put a matrix there. But the proof is really simple, because for any eigenvalue here, if you put instead of a eigenvalue of the matrix, it will be zero, just with the property. So this polynomial has the property that for any eigenvalue is zero, and if the polynomial is zero on all the eigenvalues, for example, for Hermitian case, then it is obvious that it is a zero polynomial. This is a zero matrix. can show that basically if you have this, then you can express A minus 1F, the inverse of the matrix.
If inverse exists.
Well, okay, if inverse exists, then we can express the inverse as a polynomial applied to the same f.
Okay, right.
So at least this shows that the solution belongs to sufficiently large Krylov subspace. So the natural basis for the Krylov subspace is very bad.
So you mean that, like in this case, if inverse exists, you don't need to start the formal process. You can take the characteristic polynomial, just put it there, multiply the matrix, and that's it.
Yeah, you can do that, but of course computationally this is both unstable and slow, so this is more existence result. You never use this in computations, but at least this confirms why using Krylov subspaces is a good idea. Yeah, exactly arithmetically contingent. If you are able to put a characteristic, yeah. Equation. Yeah, in exact arithmetic you can do that. Now I was thinking where the derivatives went. Yeah, the derivatives were divisions. Sorry. So all the division is here. So it's only in the leading term. All others are just multiplications. Computing the coefficients of characteristic polynomial, these are only multiplications. So it might be useful somewhere. Okay, let's go on. We have a long way to go. So first observation is that you need another basis for the Krylov subspace. Using these vectors as a basis is useless. We discussed previous time because they all converge to the same vector. So we need to orthogonalize. So the condition is really big. So this is the short illustration of how big it is. So this is again now 100 times 100 matrix. If you have just two vectors, the condition number 7, 40, a lot of numbers. So basically, well, you can show that it grows exponentially with the size. The condition number of the natural representation grows exponentially with the subspace order. So the solution, as we all know now, do not use ill condition basis, use orthogonal basis, and what we do, we just orthogonalize the vectors from the Krylov subspace by using Gram-Schmidt orthogonalization. And then we get, instead of k's, we get the first column of this orthogonal matrix, the second column, the third column, the fourth column, and so on. So the problem with this approach is obvious immediately that we need to store a lot of vectors. So in the Richardson iteration, when we do Richardson iteration, we only store 2 vectors at each iteration, but the Chever should also store only 2 vectors. And we can afford to make thousands of iterations. Using Krylov subspace directly in this form, it is not possible to have thousands of iterations because you will need to store thousands of vectors. And then you either have to truncate and start building Krylov subspace from scratch or do something else. So for the symmetric positive definite case, it's possible to avoid these problems of increasing number of vectors completely. We'll see how. But meanwhile, so if we have the Q, then we approximate the solution as x0 plus Q, and then use the variational principle, minimize the energy function, and get the answer. But in order to get formulas that do not require to store m vectors after m multiplications, we need to get what is called recurrence relations for this basis. So what we have? So let's start from this. So this is our noisy relation, which we will figure out what it is. But let's start from illustration. So the vectors are quite special that we have here. The vectors that are quite special that we have here. So K0, K1, and so on, they're the first trial factor, the second trial factor, the fourth, the first, second, third, but 0, 1, 2. So, and if we apply the matrix A to each column of this matrix, we get the next trial factor. This is very obvious relation. A times the first trial factor is the one shifted. And what we want to do, we want to express each of this vector in the same basis that was here, plus some correction term. And the only correction term we will have will be in the third vector, which was not present in the original Krylov subspace. So how we do that? We write this as a, so we write each column of this matrix as a linear combination of these columns. And this is formalized as a product of this matrix times 3 times 3 matrix. But additionally, we put here some unknown parameters which we will determine later. So this part of the matrix is determined uniquely because, but here we can subtract anything what we want. So this is the A times K equals K times something plus correction here. So in the matrix form that is written as A times K3 equals K3 times Z. So this is an inverse shift matrix. So this matrix, if it takes a vector, it shifts it, plus some last column, plus a rank 1 matrix which is non-zero only in the last column. Okay? So then what we do orthogonalization of the Krylov subspace, and orthogonalization of the Krylov subspace is written as QR, where Q is orthogonal matrix and R is so this is the starting point. And we can generalize it from 3 to arbitrary dimension. K times MM, K times Z plus correction. Then we factorized the Krylov matrix. So our goal is to get some equations for Q. So that's our final goal. And in order to get, we don't provide any algorithm yet. We want just to get some recurrence relations. So we have QR factorization of the